Alright, so let's suppose we have an object here, a particle if you like, and then applied to this object are a bunch of forces. Now our good friend Newton tells us that if we sum up all the forces, add them together, then this is equal to mass times the acceleration of the object. And in this video what I want to do is do a little something different with this Newton's second law. I'm going to take all these forces, add them up together as I said, but this time I'm going to integrate them with respect to time. And it's going to be a definite integral from time, I'll call time 1, to another time I'll call time 2. And of course, if I do that on one side of the equations, I have to do the same thing on the other side. And here's what I get. Yeah, well the right-hand side is kind of easy. We're integrating acceleration with respect to time. So by definition, that's a velocity, but of course we're integrating from time 1 to time 2. And by the way, I'm assuming mass is constant right now. So this becomes mass times velocity, and we're integrating, the limits of my integration are time 1 and time 2. So this is mass times velocity at 2 times velocity at 1, like so. And then the stuff on this side, this is the integral of my forces. And this one has a special name. I'll call it the impulse. In fact, I don't just call it the impulse. That's what everyone calls it. So we've got this nice little relationship that says the impulse, and going from time 1 to time 2 is equal to mass times velocity 2 minus velocity 1. So in the end we get something that I like to write in the following way. So mass times velocity 1 plus this impulse, it's integral from time 1 to time 2 of the sum of the forces with respect to time. This is equal to mass times velocity at 2. Now this mass times velocity, that has a name. It's called the linear momentum. So let me write it down. And it's the linear momentum at time t1. And of course on this side we have linear momentum at time t2. And of course we've already labeled this integral that's in the middle here. That thing is the impulse. And what we have is an expression that is essentially our impulse momentum principle. Now there's a couple comments I want to make about the impulse momentum principle. First of all, it is a vector principle. And what do I mean by that? It's a relationship between vectors, right? M times v1, that's a vector. Sum of the forces integrate over time, that's a vector. M times v2, linear momentum here, that's a vector. So it's a relationship between vectors. You got vectors on both sides of the equation. And this makes it different than work energy principle, you may recall. Remember in work energy, if you calculate the work and going from some point A to some other point B, it is also an integral of a sum of forces. But you take all these forces and you take a dot product with dr, right? It's an integral over space. And you integrate from some point A to some point B. But because we take this dot product, it becomes a scalar, right? And then you had the work equal a change in kinetic energy, right? And for each of these kinetic energies is 1/2 mass times speed squared. Not velocity, but speed. Speed is a scalar. So in work energy, we had a purely scalar principle going on. In contrast, impulse momentum is a vector principle. Also, in the impulse momentum principle, we're integrating over time. Again, very different from work energy, where that work is an integral over space. And finally, I'll observe that this impulse produces a linear change in velocity. Right? What I mean by that is velocity appears in here linearly. We don't see v squared. Whereas in work energy principle, this kinetic energy is a speed squared, right? So important differences. Now one of the best uses for the impulse momentum principle is if you have two or more objects. So let's say I have two just for the sake of simplicity, and let's call this object A, and let's call this other one object B. And furthermore, let's say I have a bunch of forces acting on these objects. So in object A, I have FA1 and FA2. Object B, I have FB. And let's suppose these two objects are interacting with each other too. Maybe they're connected by a spring. Maybe they're in contact with each other. Something like that. So I'll call lowercase FAB. That'll be the force on object A due to object B. And similarly, FBA would be the force on object B due to object A. So now if I write out the impulse momentum principle for object A, I get mass times velocity of object A at time 1 plus the total impulse on A. So here we're looking at all the external forces acting on A. We're summing all those up. We're integrating with respect to time. And this gives me the total momentum of object A at time 2. And of course I can do the exact same thing for object B. And don't forget that these two integrals are definite integrals. I'm going from time 1 to time 2. Now the next thing I do might seem a little crazy at first, and perhaps it is a little crazy. But we'll try to make sense of it. I'm going to take these two impulse momentum principles and I'm going to add them together. So I'm going to take the entire left-hand side of the first one and add it to the entire left-hand side of the second one. Right? And that should give me, if I keep it all on the left side, it should give me the sum of these two, right? So let's write it out. Actually, before I write it out, let me include one very important thing I completely forgot about. Particle A and particle B here, they could have totally different masses. So maybe I should be careful about what the masses is. So here's massive A. There's massive A. And this one's massive object B, massive object B. Can't leave those out. Alright, now let's go back to where I was. So add these things together. I got massive A times velocity of A at time 1. So there's the linear momentum at time 1 of particle A. And of course we get linear momentum of particle B. And then I'm going to add in a sum of a whole bunch of forces. And I'm going to write those forces out explicitly. So I'll write integral from time 1 to time 2. And just the sum of all these forces in the on object A. So I have FA1, I have FA2, I have FAB, I have FB, and finally FBA, right? And I'm integrating all of those, or the sum of all those with respect to time. And what does this give me? This gives me the total momentum at time 2 of the two particles. Now something rather curious happens in here. Notice that I have FAB and FBA. Remember, FAB is the force on object A due to object B, and likewise the force FBA is the force on B due to A. And I didn't tell you exactly what those forces are. I said there might be a spring connecting these two things. There might be a force of impact. It's something, right? But for me, at least in this context, we don't care what it is. All we care is it's a force between two objects internal to my system. Here I have, if I think of these two objects as my system, and things between the two objects is inside, and forces coming from outside is external to the system, then these little f's are internal to the system, and more importantly, because of Newton's third law, these forces have to be equal in magnitude and opposite in direction. Again, that's Newton's third law, and we don't argue with the physical laws. We take them as absolute truths. So this tells me that the sum of these two forces have to add up to 0. Remember, they're same magnitude, opposite direction. So if I take this force, FAB, add it to that force, FBA, has to be 0. They cancel each other out. So in the end, this is what we get. This piece right here, it's the linear momentum of the system at time 1. And over here we have the linear momentum of the system at time 2. Now when I say system, what I mean is the collection of the two particles, A and B. It's the linear momentum of both of those combined. And this piece right here, what's interesting is that only the external impulses matter. So impulses due to these internal forces, the little f's here, do not appear in my equations, do not appear in this expression. So these impulses, these forces of interaction, do not change the linear momentum of the system. That's cool. And we'll see how that principle, or how that result here, can help us solve some problems.